Okay, so now to wrap up this lab, I'm going to talk about a little bit about what we would expect to see and what we've learned from the data that we've gotten. So if you did this data carefully, I would expect to see that when you did this graph of the velocity and the height using the tools up above, that you would see a relationship that looks kind of like this. You would see a curve out of the data, and the data points would fit somewhere kind of close to that curve. It would clearly not be a straight line. If it had been a straight line, you could say that the velocity is proportional to the height. That means if you double the height, you double the velocity. What we found through looking at this is that's not what happens. It's a more complicated relationship. It turns out that actually the velocity is proportional to the square root of the height. That's a little bit hard to think about. We're maybe a little bit less familiar with square root functions, but that is what this shape is. It's a square root. It's maybe slightly easier to think about it by squaring both sides of that. You get velocity squared is proportional to the height. So that means if you double the height, it will double whatever the square of the velocity will turn out to be. That's maybe like slightly easier to think about, but it's still maybe a little bit foreign for most of us because we're not really used to thinking about square functions and square roots and stuff. Okay, so to make this make sense, let's think about what's going on in terms of the energy of the system. So what you're doing when you're picking up that frozen hockey puck and dropping it is you're giving it potential energy by raising it up in the air. And then when you let go of it, that potential energy gets turned into kinetic energy as it falls, as gravity causes it to speed up. So you're taking potential energy and turning it into kinetic energy. And what we're seeing in this relationship in the data is basically the relationship between the potential energy up at the top, which is in the form of the height, and the kinetic energy at the bottom, which is in the form of the velocity. Okay, and then this equation relationship that we're seeing with this graph is telling us like something very specific about that relationship. So if you look in the book and some of the other materials that I've given you, you'll see potential energy of an object that's lifted up is equal to the mass of the object times the strength of gravity on the planet that you're on times the height that you lift it to. So that's saying if you double the height of something, you're doubling how much potential energy it has. If you double the mass of something, it doubles how much potential energy it has. Kinetic energy, on the other hand, is 1/2 the mass of the object times the velocity of it squared. That means if you double the mass of something, it has twice as much kinetic energy. But if you double the velocity, it has 4 times as much kinetic energy. So the velocity has a bigger effect on the total amount of energy than the mass does. What we're basically doing, we're turning all the potential energy up at the top of that ramp into kinetic energy at the bottom. So that means the potential energy you had, all of it, is now all kinetic. So that means that mgh at the top is equal to the 1/2 mv squared at the bottom. It's important that you think about those as being different moments in time. There's only potential energy at the top. There's only kinetic energy at the bottom. So all of it gets turned into the other form. Okay, if we rearrange that relationship, basically I'm going to solve for the velocity. Okay, well I see that there's a mass and a mass on both sides of that equation, so they cancel out. And then if I want to get the velocity by itself, I'm going to move that 1/2 over to the other side, and you get 2gh equals v squared. And then if I want to solve for the velocity, that means what I want to do is I want to take the square root of both sides. And I'm going to flip it around so it's easier to see. That tells me, changing the colors again, the velocity is the square root of 2gh. Well, hey, there's that square root that we're seeing in this graph. The fact that this is a curve like that is telling you there's a square root relationship between the velocity and the height, and this is why. Okay, this little bit of math algebra that I've done here tells you why that shape is a square root shape. It also tells you something really interesting, that it doesn't matter what mass the puck has. It will still have the same final velocity if you dropped it from the same height. The things that determine the velocity when it gets to the bottom are the height that you drop it from and the strength of gravity. But the mass doesn't matter. And so if you compare notes with somebody else who did the other mass than you did, you should both see you got the same results for the velocities at the different heights, or at least very close to it. So the height matters, the strength of gravity matters, but the mass doesn't matter. And then finally, what we're seeing in this experiment is the relationship between potential energy and kinetic energy. If you lift something up, you give it potential. If you drop it, it turns into velocity, which is kinetic energy. A practical application of that is something like using a waterfall as a source of energy to turn an electric generator. So the water has potential energy up at the top. As it falls, that potential energy turns into kinetic, and then it makes the generator spin, which turns that kinetic energy into electrical energy, which then can get used for many other purposes. Okay, thank you very much. I hope that lab was interesting. And make sure that you're thinking about how to apply those concepts to the rest of the work that we're doing.